Hi guys, in this lesson we're going to be looking at some application of 3D vectors. So in the last video we just looked at what vectors look like in 3D and how we can represent points in 3 dimensions. Today we're going to be looking at how we can represent shapes in 3 dimensions and how we can use our knowledge of vectors to help us solve problems involving vectors in 3 dimensions. What I've got here is I've got a diagram that shows this rectangular prism. We know that the length of AB is 6 centimeters. We know that the length of BC is going to be 4 centimeters. And we know that the length of CG is going to be 3 centimeters. That's just the length, width, and height of the rectangle, respectively. It wants us to calculate the angle of FDB. And we also need to calculate the angle between the skew lines DB and HE. Just remember that skew lines are lines that are not parallel and do not intersect each other. So that only applies in 3 dimensions. Right, so we need to calculate angle FDB. So the first thing we need to do is we need to assign all of these letters, all the letters that we're interested in, some sort of coordinate. I'm going to assign D as being the origin. Now you can assign D to be whatever you want because it's in 3-dimensional space and you can move it around. But just remember that A, B, C, D, E, F, G, and H all have to be relative to that point that you give D down there. I could have made H the origin, I could have made E the origin, but I'm just going to make D the origin because it's going to make my life just that little bit easier. What I'm going to do is I'm just going to give us a little bit of a map to follow, and going up and down is going to be Z. If we go in this direction, we'll call that X, and if we go in this direction, we'll call it Y. Now, we know that AB is 6 centimeters. We know that BC is 4 centimeters, and we know that CG is 3 centimeters up there. We can use these lengths to help us figure out what the coordinates of A, B, C, D, E, F, G should be relative to each other. We just want F, D, and B. Well, if we look at F, we know that to get to F, we have to go 4 along this direction, 6 along this direction, and 3 up. So it's going to be 4, 6, 3, if we just use those coordinates there. And B, we need to go 4 in this direction and then 6 in this direction, but we're not going up or down. So that's just going to be 4, 6, 0. So now we've got our D, F, and B, and we can use that to help us figure out what the angle between them is going to be. So first of all, what are we looking for? We're looking for that angle in there. And we're looking for what this angle theta is going to be. We need to determine what the vector DF is going to be and what the vector DB is going to be. So for DF, we take point F, which is 4, 6, 3, and we take away point D, which is 0, 0, 0. You see why making D the origin is going to make our lives a bit easier. So the vector DF is 4, 6, 3. Now we have to work out the vector DB. So the vector DB is going to be our 4, 6, 0, take away our 0, 0, 0, which is going to give us just 4, 6, 0 there. So that makes our life easy. Now we can use the dot product, which we learned before. So the dot product between DF and DB equals the modulus of DF times the modulus of DB times cos of theta. So that's what we're looking for, that angle theta is going to be out there. So we need to find out what the dot product between DF and DB is going to be. So we're going to do 4 times 4 is 16, plus 6 times 6 is 36, plus 3 times 0 is plus 36, which gives us 52. The length of DF is going to be the square root of 16 plus 36 plus 9, gives us 61. And the length of DB is going to be the square root of 16 plus 36, which is 52. Cos of theta. Now to get rid of the square root of 61, square root of 52, we just divide that on the other side. And then we take the cos inverse of that there, which gives us an angle of 22.6 degrees. The angle of FDB is going to be 22.6 degrees. Alright, so in the second part of the question, we want to calculate the acute angle between the skew lines DB and HE. So again, what we need to do is we need to figure out what all the coordinates of H, E, D, and B are going to be. We know that B is 4, 6, 0 from the previous question. We know that D is 0, 0, 0. H is 0, 0, 3 because it's going 3 up from the origin. and E is going to be 4 across, 0 in the y direction, 3 in the direction up there. What we need to do now is we need to figure out what the vectors dB and HE are going to be. We're looking for those two vectors. Okay. So for vector HE, we're going to do vector E subtract vector H, and that gives us 4, 0, 0. And vector dB from the previous question, 4, 6, 0. And again, we're going to be using the dot product to help us find the angle between the skew lines. So what we need to do is we need to find the dot product between HF and E. So it's 4 times 4 plus 0 times 6 plus 0 times 0, which is 15. Then we have to multiply the length of HF by the length of dB times cos of theta. So we end up with 16 root 52 cos of theta. And again, we'll find cos inverse of 16 over root 16 times root 52, which is root 800 there. And that gives us an acute angle of 56.3 degrees, which is what we're after. Now, it's actually quite hard to see what we're looking for when we're looking for the angle between skew lines like this. I just want to remind you that the vector dB is actually going to be the same as the vector HF, because it's the same magnitude going in the same direction. So if we just moved vector dB up to vector HF, they're actually the same vector. The angle we're looking for is actually that angle there. When we find the acute angle between the skew lines dB and HE, it's actually that angle there that we're finding. And if we did a top-down view of what that looked like, it's that angle over there. If we had a top-down view of the angle between those skew lines. All right, let's move on to the next one now. If A is 2i plus j minus k, B is that vector, C is that vector, and D last vector there, we want to write D in the form of lambda A plus mu B plus sigma C, where lambda, mu, and sigma are all scalars. So first things, A, B, C, and D are all in component forms, not written in vector form, they're just component forms. And we want to write D as a linear combination of A, B, and C. So this is where we come to solving systems of linear equations. I'll go through how to do that manually in a later lesson. So for today, we're just going to be using the class pads to help us solve that. Let's just set up the question. So we want to write vector D, which is 9, 5, and 2. See, I've put it in column vector form because it just looks a bit nicer and it works a bit better with me. So D is equal to lambda times vector A plus mu times vector B plus sigma times vector C. And I'm just going to write that out as 3 sets of linear equations. So we've got 9 equals 2 lambda plus 3 mu plus 1 sigma. And then we're going to have 5 equals lambda minus 2 mu minus 2 sigma. And then we're going to have 2 equals minus lambda plus 4 mu plus sigma. So this is what we call a system of linear equations, and we're trying to solve for lambda, mu, and sigma. So we want to know what linear combination of these will give us vector D. This is a linear combination because we're adding a scalar multiple of each of these vectors. So to do this, what we need to grab out is our class pads. So your class pad, go to math 1, and we've got 3 equations. And we're just going to type in those 3 equations. So we're going to get 9 equals 2x, I'll type it in there, 2x plus 3 lambda plus sigma. And obviously I'm using x, y, and z because it's just nicely on my keyboard. Okay. Z, and we're solving it for lambda, mu there, and we get 3 to negative 3. So it's not too bad of a question to do if you've got your class pad handy. So I did that earlier, and what we should get is 3 to negative 3, which is what we had before. So if we wanted to write D as a linear combination of A, B, and C, it would be 3 lots of A plus 2 lots of B minus 3 lots of B, which would give us that one there. But it says it wants us to write it in the form of this. So that's the answer there. Don't just leave your answer as lambda's 3, mu is 2, and sigma's -3. All right, let's move on to another question. Point A has a position vector of 1, 5, 4, and B has a position vector of 6, 5, -6. Just remember that position vectors are usually given from the origin. It wants us to find the position vector of the point P that divides AB internally in the ratio of 2 to 3. I'm just going to go over what that means. So we've got vector OA, and we've got vector OB, and we want P to divide AB internally. If it's internally, it means it's in between at some point. Now, we know that it divides it internally in the ratio of 2 to 3. So 2 parts there and 3 parts there, making 5 parts in total. So we need to find out what that position vector OP is actually going to be. So how can we get there? Well, we can go up along A, and then we'll go 2/5 of the way from A to B, because if it's dividing it in the ratio of 2 to 3, there's 5 parts in total, and we want 2 out of those 5 parts to get from A to P there. So the vector OP is going to be O to A plus 2/5 of the way from A to B. So what is this vector A to B over there? Well, that's just vector B minus vector A. Remembering that this is vector B and that's vector A over there. So we're just going to do our 6, 5, -6, take away 1, 5, 4. And that's going to give us 5, 0, -10. Right, so we know what that vector is going to be over there. So vector OA is 1, 5, 4 plus 2/5 of that will give us this vector over here. Yes, I am switching between row vectors and column vectors. That's just a spacing issue that I'm having working through these PowerPoints. So if you see me switching through them, usually you stick to one kind, but I'll just be switching between them depending on how much space I've. All right, so we know that vector OP is 3, 5, 0. We could stop there. Let's just see if we're right though. Is this the only way for us to get from O to P? Well, we could go from O to B and then go 3/5 of the way from B to A. So let's examine that kind of method. So again, it's the exact same principle. So we're going to go from O to B plus 3/5 of the way from B to A. Now, instead of doing a plus 3/5, we could go minus 3/5 of A to B. Because if A to B is traveling from left to right, to go from B to A, we have to go minus the direction of A to B. Which is why it's minus 3/5 of A to B. We could have worked out vector BA, but because we worked it out before, it's not necessary. It's also good to know that if you're going in the opposite direction of a vector, you just take the negative value of that vector if you want to travel in the opposite direction. Alright, so vector OB is 6, 5, -6, and we're going to take away 3/5 of 5, 0, and -10, which gives us the same vector we had before of 3, 5, and 0. So we know we've done it right. So find the position vector of the point P. The position vector of point P is going to be 3, 5, and 0. And I'm going to make sure that I write my answer in column vector form, because that's the way that the question has given all of their vectors in. Alright, so in the last question, we looked at dividing a line segment internally in some ratio. In this last question we're going to divide a line externally in a ratio of m to n. So I'm doing two things here. We're going to go through a bit of a proof, and we're also going to be looking at what dividing a line segment externally is going to look like. So again, we've got vector A down there, and I've just changed orientation just to help with a bit of spacing on the PowerPoint. So we've got our position vector A, we've got our position vector B, and if we're doing it externally, I'm just going to put my point P down there somewhere. And what else we know? We know that the length of A to P is going to be n, and the length of B to P is going to be n, because it's divided externally in the ratio of m to n. And we're going to use the same principles that we used before to help us solve this question as we did dividing it internally in a ratio. Just to make the notation a bit easier, I'm going to call vector OA just A, I'm going to call vector OB just B, and I'm going to call vector OP just B. That's just going to help with the syntax. Alright, so how do we start with these sort of problems? We're just going to start with writing out what vector OP could be. So I've just written there that vector OP, which is the same as P, is A. So we'll go down vector A, and then we'll go M lots of AB over M take N. I'm just going to explain this quickly. I'm going to write it a little bit differently here. So P equals A plus M lots of AB all over M take away N. What you might remember from before is that if you look at M take N, M take N is actually the length of vector AB. So I could write that as A plus M lots of AB all over the modulus of A to B. Right, so this is actually a unit vector. So this vector has a length of 1, but it goes in the direction of A to B. To get from A to P, we needed to have a length of M. All right, so what this is doing is that we're going to multiply the unit vector of A to B by M. That gives it a length of M, and it's in the direction of A to B. So all this jargon over here is just saying that we're going to go down vector A, and then we're going to go M units times the unit vector of A to B, because that's going to give it a length of M in the direction of A to B. All right, and we're just going to rearrange that now. So I'm going to write everything in terms of A, B. So this vector AB over here. So the first thing I'm going to do is I'm going to move my A to the left-hand side. So I'm going to have P take away A is M over M take away N times that vector AB. And then we have to multiply the left-hand side by M take N. So I'm going to get P take away A times M take away N. And we'll divide it by the scalar M. And that's all going to equal vector AB over there. Now that's not the only way to get our vector P. Another way to get vector P is we could go down B, and then we could go this much across in the direction of A to B. So again, like before, this bit over here is actually the same as N times vector AB all over its length. Okay, so this is a unit vector, which means it has a length of 1 in the direction of A to B. But we don't want the length to be 1, we want the length to be N, because to get from B to P, we're saying that the length is N. So this bit over here is just saying we want a unit vector in the direction of A to B, but we're going to multiply by N because we wanted to have a length of N. And again, rearranging that, just like we did with the previous one, we can get AB is P take B times M take N all over N. All right, now you'll notice that what I've done here is I've linked my P, my A, my M's, my N's, and my B's with two equations. As you can see here, we've got M times B minus N times A all over M take N. What you'll also notice is that this AB must be the same as that AB over there. So if those two AB's are the same, then that means that this part of the equation must be the same as that part of the equation over there, which is what I've shown down here. What we're going to do now is we're just going to do a bit of rearranging. I'm going to multiply both sides by N. I'm going to multiply both sides by M, which will give us this result here, or you could just cross multiply it if you prefer that way. Then what I'm going to do is I'm going to expand and simplify, and we end up with this result over here. Now what I want to do is I want to have P by itself. So what I'm going to do is I'm going to move this P to this side of the equation, which means that I'm going to move that B to this side of the equation. Once we've done that, what you should end up with is Bm minus An equals Pm minus Pn. Just remember that I want P by itself on the right hand side. So the way I'm going to do that is I'm just going to factor out the P. So I'm going to have P times M take N on the right hand side. And to get rid of that times M take N, we're going to divide both sides by M take N, which will give us this result over here. Now, we need to prove this result, not in terms of B and A, but in terms of OB and OA. Now, at the start of this, we said that B is the same as OB, and we said that A is the same as OA. What I've done there is we've shown that our vector P, which is OP, is the same as MB minus NA all over M take N. And we know that B is the same as OB, A is the same as OA, and this proves the result.